I've proven the first part of the Darboux theorem, which says that if a function, any function, as long as it has antiderivative over a closed interval, we call this little f of derivative function. Then for this little f, it takes all the values in between little f of a and little f of b, the intermediate value theorem property. If you take any value in between those two values, there is always some constant inside this open interval whose functional value happens to equal to exactly to alpha. I've done that. In this video, I'm going to prove a second part, which says there's no discontinuous points of type 1 for derivative functions. So here I'll just use one of the many examples. Let's just use say, for example, the function is discontinuous at x0. Let's say the function has a left-hand side limit, which is a finite number. Let's say this is my left-hand side limit, but the functional value is not defined here. There is a hollow point right here. But the function somehow also has the right-hand side limit, the same as the left-hand side limit, but the functional value is actually defined perhaps up here. So here is f of x0. So down here there is the limit L. So here's one example. There are some other examples, but here I'm just going to focus on this one, and I'm not going to discuss in details about the type 2 discontinuous points. So when I'm done with those two, I'm going to use the result to prove there's no relation between antiderivative and Riemann integrability. In a future video, I will give some counterexample of where a function has antiderivative, but it is not Riemann integrable. I'll also give an example where the function is Riemann integrable but doesn't have antiderivative. So I'm going to prove by contradiction. First of all, I assume that little f has some antiderivative over AB. Right, so maybe here's A, somewhere here there is B, I don't know, there's B. So I'm going to also assume that the function little f actually has discontinuous point of type 1 of this type where the limit exists on both sides. X approaches x0 of f of x is equal to L, where L is actually strictly less than f of x0. F of x0 is way above, up there. So I'm just going to use the right-hand side limit. I'm going to let x approach x0 from the right-hand side without loss of generality. In fact, I'm just going to use a small neighborhood. So the meaning of limit is that when x is close enough to x0, then their corresponding functional value should also be close enough to this L. Right, perhaps I can choose epsilon of various epsilon of maybe just half of the distance of this distance. Maybe this epsilon. And here's my restriction. Here's my restriction. So according to this epsilon, maybe I can use here. So here, this point is my x0 plus delta. Right. So as long as x lives in this right-hand side neighborhood, then I can make sure the functional value is strictly less than this point. close enough to this point, but strictly lower than this point. And this point, I call that middle point, right? The middle point between this and that. So this is actually half of f of x naught plus L. That's my middle point, right? So in fact, I just chose epsilon to be half of f of x naught minus L in this case. Right? Epsilon is exactly half of the distance between this point and that point. That is, only this distance is my epsilon. Right? Epsilon. Therefore, functional value close enough to this value, but far away from here. Right? Smaller than that. So indeed, there exists some. So for this epsilon, right? For this epsilon, f of x naught minus L. Right. There exists some delta as long as I'm using the right hand side. So as long as x is larger than x naught, but smaller than x naught plus delta. As long as x is within here, x naught up until x naught plus delta in here, right? Then I can make sure that, right, in this neighborhood, in other words, as long as x minus x naught is larger than 0 and smaller than delta, then all the functional values of x can be smaller than, strictly smaller than this point. That's my middle point. Right? Middle point. Half of f of x naught plus L. I don't even have to worry about this point, because all I need to show is that fx is small enough, lower than this point, but larger than this point. I don't even have to worry about this point. All I need is to show that functional value is lower than this point. That's all I need. So in other words, as long as x lives in this neighborhood, then their corresponding functional value can be far away from this point, strictly far away, strictly lower than this point. Of course, lower than this point as well. Lower than f of x naught as well. Obviously. So, then I'm going to, for example, so here's x naught, there is x naught plus delta. I'm going to fix another point, x1, in between x naught and x naught plus delta, fix it. So I'm going to fix x1. Therefore, x1 is strictly larger than x naught and strictly less than x naught plus delta. In other words, x1 minus x naught is strictly larger than 0, but strictly less than delta. So therefore, meaning the fixed point x1 still lives in this neighborhood, deleted neighborhood, right-hand side deleted neighborhood. So therefore, f of x1 is less than half of f of x naught plus L. Right? This is from this result. As long as x lives in this neighborhood, then the functional value is always less than this value. right? So therefore x1 is a fixed point. As a fixed point that lives in this neighborhood, its functional value, of course, is according to this, is still less than this value, right? So therefore, that is less than f of x naught. So therefore, x1 and x naught are both fixed. In between those two fixed values, any value should work. Therefore, this is a fixed value. Should also work. The intermediate value theorem should still apply. So, for this particular constant, there has to exist some fixed c that's inside the open interval of between this point and that point, and x naught, x1, right? This open interval, so that f of c is in fact equal to this constant, half of f of x naught plus L. That's the according to the intermediate value theorem for derivative functions, right? Assuming it is a derivative function, then this intermediate value theorem applies. Right? Fc is equal to exactly this value that's in between this and that. So then I'm going to show that. First of all, C is in between those 2 points, right? C is inside this open interval, right? C is right somewhere here. So therefore, from the graph, it's easy for us to prove that C is in fact still larger than x naught, less than x1. x1 is less than x naught plus delta. Therefore, C is larger than x naught, but less than x naught plus delta. In other words, C still lives in this deleted neighborhood, right-hand side, deleted neighborhood. So therefore, C is still larger than x naught, but smaller than x naught plus delta. Right? In other words, C minus x naught is still larger than 0, less than delta. C still lives in this deleted neighborhood. Therefore, like I've just shown, that as long as x lives in this deleted neighborhood, right-hand side, then its corresponding functional value is definitely always smaller than this. So therefore, f of c is smaller than this as well. Right? So f of c is smaller than half of f of x naught plus L as well. So here's the contradiction. First of all, I use intermediate value theorem to show that f of c is equal to this, but now I show that f of c is less than this, which is entirely impossible. So this already contradicts the intermediate value theorem. Right? This inequality already implies that f of c can never reach this constant. Right? Already makes my intermediate value theorem invalid, which means it already contradicts the intermediate value theorem. So here is indeed a contradiction. This is indeed a contradiction. So I'm done. So in other words, my assumption is false. In other words, if my derivative function is somehow discontinuous, then this continuous point can never be discontinuous point of type 1. This is only one example, one case. In the other cases where the functional value is defined somewhere below down here, it will be similar discussion. In some other cases where the function has left-hand side limit, but have a right-hand side limit also, but left-hand side limit and right-hand side limit happen to be different. And maybe here is the left-hand side limit right here, but right-hand side limit may be up here, right? As x approaching this x naught from the left-hand side, the limit is down here. But when you approach from the right-hand side to x naught, the limit is actually up here. So therefore, you have different limits from the left and from the right. So that's also another possible case, but it'll be very similar discussion. So I'm done with the second part, right? So that there cannot be discontinuous points of type 1 for derivative functions. And in a future video, I will prove this one. So there's no relation between antiderivative and in Riemann integrability. So from the second part, that means if it's a derivative function, it doesn't even have to be continuous over a closed interval. Doesn't have to be continuous for it to have intermediate value theorem property. So which means continuity over a closed interval is only a sufficient condition for a function to have intermediate value theorem property. It is not a necessary condition, looks like. So in the end, the essence of the intermediate value theorem is in fact not continuity over closed interval, but connectedness. It is in fact connectedness. This is the essence. So in the future, I will be discussing the connected sets.